All right. Well, first of all, I'd like to thank all the organizers for making this meeting possible. And I think since this is the last talk, we should all show our appreciation to Raoni and Jonas and Chris and Dacian and everyone involved in organizing the meeting. So look, our sincere thanks. Well done.
Thank you.
So it's been a great meeting up to now. At least it's only the last talk things go down the tube. So what I'm gonna talking about?
We're just in front of the abysm.
That's right, exactly. We're just staring at right. Yeah. So what I'll be considering is the issue that modality plays, the roles that it plays in quantum mechanics, right? And I think it's clear that it's invoked in the impossibility of certain quantum configurations, the necessity of certain radioactive decays, or the probability, which itself a modality with degrees of certain experimental outcomes. So there's no doubt the modality play many significant roles in the theory. Right? So what I want to ask is, what is the source of such modality? Now, Bob Hale asks that kind of question in the context of logic and metaphysics. And in another paper, I'm going to engage with what he has to say about those things. So today I'm going to see what take should be developed on that issue in the context of quantum mechanics. So one of the questions here is whether the necessities involved in quantum theory should be explained by other necessities or whether they can be explained by contingencies. Now, Alistair Wilson, in his recent book, identified two such answers to those sorts of questions about the sources of modality. One of them, necessity first approach, will take the necessary as being basic, right, and use it to explain the contingent. The other approach, contingency first view, would do the reverse, would take contingency in a way as being basic, and what needs to be explained is the necessary. Now, in this talk, I'm going to identify two roles among the many roles the modality plays in quantum mechanics. I'm going to identify two. One involved in the characterization of the quantum domain, and another regarding the specification of the states a quantum system can be in. So both, I'm going to try to indicate, are central to the theory. And in the context of these two specific roles that I'm going to address the issue about the sources of modality in quantum theory. I'm going to offer what I call an empiricist modalism that's going to insist that the source of modality is found in the relevant properties of the objects under consideration, relevant electrons, bosons, and so on, while resisting several attempts to account for the source of modality that rely on conventions, models, or essences. So I'm going to try to resist conventionalist approach, model-based views, and essentialist approach. And overall, as it becomes clear, the view that I'm favoring is a form of a contingency first approach, where contingency is first, and the necessity to extend that it obtains, it comes later. Well, this is part and parcel of an empiricist view, right? The world of the empiricist is a world of contingency, right? The world in which anything is possible, in a way. So let's see how this can be worked out. As I said, I'm going to focus on two roles, initially two roles the modality plays in quantum mechanics. The first one is in the characterization of quantum mechanics itself, right? And I want to say that what quantum mechanics relies ultimately on the modal character of the objects under study. Why is that? So look, for example, at the way that Dirac, in his celebrated book on the principles of quantum mechanics, how he himself presents what quantum mechanics is. So he says, quantum mechanics may be defined as the application of equations to motion, equations of motion to atomic particles. Now, on the face of this, this may seem to be a completely non-modal way of characterizing quantum mechanics, right? As I'm going to try to indicate, this appearance is deceptive. If we dig a little bit further on what exactly an atomic particle is in the specific way that Dirac understands that. So what Dirac offers here is an account in terms of the relational properties of the particle's absolute size. So it's very important for him to say, look, we need to understand that there is a certain notion of size that is absolute in terms of which we're going to understand what those particles are. And in this way, he actually bypasses altogether the thorny issue of the constitution of subparticles. So in that way, his account of what quantum mechanics is actually fairly general. It doesn't tell you what specific theory of quantum mechanics one should adopt. So let's see how he does that. He starts by contrasting classical and quantum explanations. He tells us in a classical explanation of the constitution of matter, one would assume it to be made up of a large number of small constituent parts, and one would postulate laws for the behavior of these parts, from which the laws of the matter in bulk could be deduced. So far, so good, the familiar kind of reductionist picture. And he continues, this would not complete the explanation, however, since the question of the structure and stability of the constituent parts is left untouched. So you can always ask further questions, right? Okay, these further parts, what are their structure? How stable are they? And to go into this question, Dirac tells us, it becomes necessary to postulate that each constituent part is itself made up of smaller parts, in terms of which its behavior is to be explained. It looks like we're basically passing the bucket here, going into smaller and smaller constituents. But there is a limitation in this process. He tells us there is clearly no end to this procedure, so that one can never arrive at the ultimate structure of matter on these lines. So long as big and small are merely relative concepts, it's no help to explain the big in terms of the small. It is therefore necessary to modify classical ideas in such a way as to give an absolute meaning to size. So what Dirac realizes right here is there's a need to identify this absolute notion of a size, so you can properly characterize what are those small parts that quantum mechanics is supposed to describe. And in the end, this absolute characterization of size is required to specify the nature of atomic particles. In order to do that, Dirac considers the nature of observation and the fact that it requires an interaction between the object observed and some external influence. So he tells us, at this stage, it becomes important to remember that science is concerned only with observable things, and that we can observe an object only by letting it interact with some outside influence. An act of observation is thus necessarily accompanied by some disturbance of the object observed. Note already the use of modality here, okay? The act of observation is itself a modal act, necessarily accompanied by some disturbance of the object observed. We may define an object to be big when the disturbance accompanying our observation of it may be neglected. Again, note the modality. It's big if the observation, the disturbance may be, it's possible to neglect the disturbance, and it's small when the disturbance cannot be neglected. Again, note the modality. This definition is in close agreement with the common meanings of big and small. So it tells us it's usually assumed that by being careful, we may cut down the disturbance accompanying our observation to any desired extent. The concepts of big and small are then purely relative and refer to gentleness of our means of observation, as well as to the object being described. In order to give so Dirac wants to avoid that. So in order to give an absolute meaning to size, such as is required for any theory of the ultimate structure of matter, we have to assume that there is a limit to the fineness of our powers of observation and the smallness of the accompanying disturbance, a limit which is inherent in the nature of things and can never be surpassed by improved technique or increased skill on the part of the observer. Note what he's doing here, right? It's the nature of things that determines whether an object is small or not, right? Smallness is not an instrument-dependent property that results from our interaction with increasingly more powerful tools of observation. So that's not what. So it's not. It's by looking at the nature of things, looking at the relevant properties, not considering what our instrumental access can be improved, that we determine in an absolute way whether something is small or not. So Dirac tells us if the object under observation is such that the unavoidable limiting disturbance is negligible, then the object is big in the absolute sense, and we may apply classical mechanics to it. If, on the other hand, the limiting disturbance is not negligible, so it cannot be made negligible, then the object is small in the absolute sense, and we require a new theory for dealing with it, namely quantum mechanics. All right, I went with all of this with you so that we can then return to Dirac's original characterization, right? Recall, quantum mechanics, he tells us, may be defined as the application of equations of motion to atomic particles. And if you combine this with the account of the nature of atomic particles that we just saw him provide, what we get is this. Quantum mechanics is the application of equations of motion to small objects, right? Atomic particles are characterized as small objects, that is, to objects that by their very nature necessarily will be disturbed when under observation in a way that cannot be neglected. Now, once we spell out in the way that Dirac actually had formulated the view, I think the modal content of the characterization of quantum mechanics is now very clear, right? So the very characterization of what quantum mechanics is in the hands of one of its prominent developers, Dirac, becomes a matter of modality. So modal discourse is central for the nature of what quantum mechanics is all about. That's my first point I want to highlight. Second point, modality is also central in quantum mechanics in order to specify the states a quantum system can be in. So suppose that we have n indistinguishable quantum particles, and consider the interchange of any pair of such particles when we permute those particles with one another, right? As we all know, if the particles are totally symmetric under the interchange of any pair, they are bosons and satisfy the Bose-Einstein statistics. If the particles are totally antisymmetric, they are fermions and satisfy the Fermi-Dirac statistics, right? This is all well known. And what is interesting here is the way that Sakurai, in his very interesting book on modern quantum mechanics, sort of fleshed that out. So see what he says. An immediate consequence of the electron being a fermion is that the electron must satisfy the Pauli exclusion principle, which states that no two electrons can occupy the same state. This follows because a state like K prime is necessarily symmetrical, which is not possible for a fermion. So as you can see here, the entire description of the possible states associated with a quantum system is couched in modal vocabulary, right? So the modal content here is very prominent. Which states are possible is determined by the quantum objects under consideration, and this in turn determines the relations these objects can or cannot enter. So it's the objects that are actually fleshing out what's possible or not, according to quantum mechanics, given what these objects are. He continues, Sakurai. We see that in the fermion case, it is impossible for both particles to occupy the same state. In the boson case, for 2 out of the 3 allowed cats, both particles occupy the same state. This is the familiar possibilities, right? So we have 3 cases and 2 of them are those that are allowed. And of course, in the classical Maxwell-Boltzmann statistic case, both particles occupy the same state for 2 out of the 4 allowed cats. So those are the usual probabilities we are all familiar with. So again, what's being conveyed here in thoroughly modal terms is the possibility of occupying certain states or not, as something that is determined by the relevant quantum objects. So it's the objects that are actually establishing what's possible or not, right? They are the sources of the relevant possibilities. So what I want to now show, so after looking at these two instances, right, of the importance of modality in quantum mechanics, you should try now to see possible ways of understanding this, right? What exactly is that source of modality in quantum mechanics? I actually think, in the way, if you listen carefully to what the physicists are saying on this respect, it's very clear what the answer is. And in fact, that would be exactly the kind of modal empiricist that I'm going to be offering here. But there are other views on that matter. And so what I'm going to do now in the second half of the talk, I'm going to go over some potential answers to that question that are different from the one that I'm favoring here. See what problems they have, and then briefly sketch my own favored solution. So what are the four possible answers I'm going to be considering here? First, conventionalism, right? The source of modality is found in linguistic conventions. I'm going to list them and then I'm going to go over them. Secondly, a sort of model-theoretic approach. The source of modality is found in the models of the theory. Third, essentialism. The source of modality is found in the relevant essences. And finally, the one that I'm favoring, the empiricist modalism, the source of modality is found in the relevant objects. So let me consider each one of these options in turn. So the conventionalist insists that linguistic conventions are the ultimate basis for modality. So if you think about similar cases outside quantum mechanics, right? Why is it necessary that a bachelor be unmarried? And the conventionalists would say, well, because the term bachelor means unmarried male. And hence we have that an unmarried male is unmarried. Well, that's necessary. Therefore, it's necessary that a bachelor is unmarried. Now, the problem here is that even for this simple-minded case, it's not clear to me that conventionalism is adequate, right? Because it needs to assume the necessity of the claim that unmarried male is unmarried. And arguably, the necessity of this statement is not a matter of convention, right? But if anything, of logical truth, assuming classical logic. So again, it's not a convention here. It's the inferential underlying inferential mechanisms of logic that are actually providing the relevant modality. But that's not a matter of convention. So that doesn't work very well here. But let's suppose that somehow the conventionalist view could be made to work. Well, I think that similar worries would be present if you were to try to account for necessities in quantum mechanics in terms of conventions. Recall Dirac's formulation, right? Quantum mechanics is the application of equations of motion to small objects, that is, to objects that by their very nature necessarily will be disturbed when under observation in a way that cannot be neglected. So why? Those necessities that figure in that statement, are they a matter of convention? Doesn't seem so, right? Because the issue here is not anything about the meaning of small. They yields the necessities in question. As we saw, the necessities are the result of the properties of the relevant objects, not the terms, the way that the terms have been used, right? And Dirac went into trouble to say, look, we need to find an absolute way of specifying what the objects of the theory are, so we can properly specify the domain that quantum mechanics applies to. This is not a matter of linguistic convention. So the objects are small, and thus necessarily they will be disturbed when they are observed in a way that they cannot be neglected. That's a matter about the objects, right? The electrons that are being, for example, that are being studied, not a matter of the conventions used to define the word small. Right? So I don't think that conventionalism has any chance here. Okay. Also, let's recall Sakurai's observation. Right? An immediate consequence of the electron being a fermion is that the electron must satisfy the Pauli exclusion principle, which states that no two electrons can occupy the same state. And this follows because the state, like K prime K prime, is necessarily symmetrical, which is not possible for fermion. Now, Here, I think it's very clear that it's not the case that electrons satisfy Pauli exclusion principle due to a matter of linguistic convention, right? The principle describes features of electrons rather than linguistic usage, right? Rather, the satisfaction of Pauli's exclusion principle results from the necessary symmetry of the relevant state that precludes fermions to be in that state. So it's a matter of the relations among the relevant objects, not a matter of linguistic convention. Okay, how about the second view, right? That's the model-theoretic approach, right? So the idea is that the source of modality is found in the models of the theory. So this is a view that von Frassen briefly presents in the scientific image. Right? So he says something along the following lines. It's not possible for an object to be both red and green all over. If that's the case, that's because in the model of the color spectrum, which represents the wavelength of the various colors, in that model involves no overlap among the corresponding colors, right? The corresponding colors in the model. So the kind of slogan will be modality is a feature of the models, right? And this is part and parcel of von Frassen's attempt at diffusing commitment to there being real modalities in nature, which he thinks it's adamant against an empiricist view. I think this is too narrow a conception of modality. And I can see why empiricists, traditionally since Hume and others, want to avoid commitment to modality, especially if together with that commitment you have some kind of involvement to abstract objects, universals, and possible worlds and things of that sort. Obviously, no empiricist wants any traffic with that, right? But I think those are separate things, right? Modality, the study of what's possible and necessary, is one thing. Possible worlds, universals, abstract objects, and so on, is something quite different. Pays what the modal realist wants us to believe. So as long as we're clear separating those things, I think there is a room for modality within a perfectly empiricist view. But that's not that's not the kind of empiricism von Frassen has in mind. He has a very austere form of empiricism. But it seems to me then the way he has it, where modality is a feature of the model, he just gets the situation backwards, right? The color spectrum, understood as the wavelengths associated with the various colors, is a physical situation in the world, a wavelength out there doing their thing. The lack of overlap among the wavelengths is a physical situation. Grounds what the model represents, and it grounds what the model represents rather than the other way around. So it's the lack of the overlap that grounds the models rather than models explaining what's possible or grounding what's possible or necessary in the world, right? So that seems to me a more reasonable take on the issue. Similarly, being small rather than big, as characterized by Dirac, is not a matter of the models used in quantum mechanics. As we saw, these are properties of quantum particles, right? So they're features of the objects. They are small. Quantum particles are small in that sense. Also, if electrons must satisfy Pauli exclusion principle, this is a fact about electrons, properly conveyed in the relevant quantum mechanical models, but not determined by the models themselves. To say that the models provide the modality seems to me just to reverse the proper order of account. We're trying to understand the world. The models are ways of representing the world. The modalities have to convey, capture, or represent features of the world rather than the other way around. Okay. Now, third view, essentialism. The source of modality is found in the relevant essences. Right? So here the idea is that objects have properties, that have the properties they have, including whatever modal properties they may have, because of the kind of objects they are. So here's, for example, the way that Jonathan Lowe thinks of the issue. He tells us, look, there is a general essence and an individual essence. The general essence of an object of a certain kind, K, is what it is to be a K. And the object's individual essence is what is to be the individual of kind K that that object is, right? So general essence is just telling us something about a certain kind, what is to be that kind. But you may have an individual essence, an essence of a particular individual. And that tells us what is to be that individual of that kind, right? That object in question is. Now, it seems to me that whatever merits this view may have in general metaphysics, when you try to apply it to quantum mechanics, it will face significant difficulties. First, in quantum mechanics, it's unclear whether there are individuals. At least on some interpretations of the theory, identity cannot be applied to quantum particles, right? That's a view that Tassi and Stephen have argued persuasively. And to that extent, and the normal understanding of individuals, quantum particles are not individuals, right? So the idea of an individual essence as a result, in as much as it requires talk of individuals, is just incompatible with certain interpretations of quantum mechanics. So we cannot even make sense of a whole plethora of ways of making sense of quantum mechanics if we take individual essences in the way that Jonathan Lowe characterized them. Secondly, also problems emerge for general essence. Why? Well, how could it be determined what it is to be an electron without relying on a theory, quantum mechanics, that describes, perhaps equivocably, what it is to be such an object? That is, the question now is, all right, we need to offer, the general essence. So can we offer the general essence of an electron without relying on the very principles of the theory that we are trying to understand, namely quantum mechanics? And of course, as we know, there are huge controversies over what exactly that theory tells us about those very same objects, including if there are any of them. So can we say, for example, that it's part of the essence of an electron, that it satisfies Pauli's exclusion principle? Is this an essential property of it? Well, arguably, something wouldn't be an electron if it violated the principle, right? It would have to be some other particle. But it's unclear whether essences play, even if that much, even if the view, the essentialist view accounts for that much, it's unclear whether essences play any explanatory role over these phenomena. Let me try to explain that. So as we saw, given Pauli's exclusion principle, no two electrons can occupy the same state. Right? We also saw that this results from the fact that a state like K prime here is necessarily symmetrical, and this is not possible, for example, for a fermion. Note that satisfying the Pauli exclusion principle is a consequence from certain modal facts about electrons and the necessary symmetry of certain states. Rather than essences, it's modality that accounts for the behavior of electrons. So in that sense, it looks like the maneuver through essences is completely unnecessary, right? Because after all, it's the modality that explaining why is it that it's not possible that electrons cannot occupy the same state as Pauli's exclusion principle insists. You say, well, that follows from some modal properties that electrons themselves have, right? Because of the kinds of necessarily symmetrical states that it's not possible, say, for a fermion to be in. So again, there's no need to talk about electrons here, right? There's no need to talk about essences here. Right? It's not the essence is just being used here as a name. It's not clear that it is doing the work. The modality is. So it makes sense to give crucial role, explanatory role, then directly to the modality, just like Sakurai did in the quotation above. Well, perhaps we could try to do better, right? And I think an improvement on Lowe's view was exactly the view that we saw, yesterday, right? Thomas and Donnell, the defending with their essential dispositionalism, right? So to remind ourselves, according to essential dispositionalism, any electron X essentially has the disposition to become modally connected with respect to some property or properties with an electron or electrons when a certain condition C obtains for that electron. So basically what's the issue here is that an electron essentially has a certain disposition, right? Namely a disposition to become modally connected with other electrons. But this doesn't hold in general, right? This only holds provided that this condition C obtains. Now, what is the condition C? Well, for an electron to be in condition C is for the electron to be entangled with any other electrons where n is equal or greater or identical to 1. Okay, note, as the authors note, that what is essential here to an electron is not that it is modally connected with any other electron or electrons, but rather what is essential to the electron is that it has a certain disposition to become modally connected with other electrons, provided that the condition C obtains. All right, so that's essential dispositionalism. And what's interesting here is the way in which it addresses directly the issues about the use of essences in quantum mechanics that we saw was problematic in the way that Lowe characterized it. Now,
Otávio, have 5 minutes.
Okay, perfect. There are two concerns here. First, the proposal seems to be restricted to a particular kind of interaction, namely when condition C is satisfied, which involves an entanglement of an electron with other electrons. So we saw that that's the only condition that is, at least in this formulation, that disposition essentialism is supposed to meet. But there are, of course, as we all know, other kinds of interactions, right? Such as when an electron is absorbed by a proton in the nucleus of an atom. These interactions will also have modal force, but are not accommodated, at least not by dispositional essentialism, at least not in that version. Secondly, it's unclear what work dispositions are actually doing. If electrons must satisfy Pauli's exclusion principle, this is not because of their disposition to become modally connected with other electrons. It's because of the necessary symmetry of the relevant state, which is not possible for a fermion, right, as we saw again and again. So again, it's the modality rather than the disposition that is doing the work. So it looks like we can bypass altogether the need to invoke essences or dispositions and go directly to modality. Well, that's exactly what the empiricist modalism, the last view I'm going to consider here, suggests. The source of modality is found in the relevant objects, right? Objects have properties, including modal properties. The table in my office is breakable, given the material it's made of. That it is breakable is a modal property of the table. Similarly, fermions and bosons have modal properties. As we saw, it's impossible for fermions to occupy the same state, whereas it's possible in some cases for bosons to do so. These are possibilities or impossibility of the objects in question. As we also saw, an electron must satisfy the Pauli exclusion principle, right? So that two electrons cannot occupy the same state, and this results from the relevant symmetry of the relevant state, not possible for a fermion. All of that clearly cast out as modal properties directly of electrons, whatever they are. Finally, in terms of Dirac's characterization of quantum mechanics as the application of equations of motion to small objects, we saw that small objects are those that, by their very nature, necessarily will be disturbed by another observation in a way that cannot be neglected. These are modal properties of the quantum objects that quantum mechanics focuses on. So I'm taking seriously the way in which quantum mechanics itself tells us, right, about how modality is entering into the picture. And empiricist modalists would emphasize those things and take them seriously for what they are. So according to modalist empiricism, modality is primitive, right? There's no attempt to reduce the modal to the non-modal, right? Something that I don't think can be done in any case. I argue for that in my work with Scott Tsiolkovsky. So the kind of reductions that modal realism aims to provide with possible worlds ultimately, end up requiring modality, so they don't ultimately succeed, right? And it's the appeal to primitive modality that makes this proposal modalist, right? So you're taking primitive, since you're stuck with it, you might as well take it as your starting point, right? As I argue for elsewhere. Note that modal considerations in quantum mechanics come in very naturally, both in the characterization of the quantum mechanical domain and in the specification of the states a quantum system can be in. So that was the point of the first part of the talk. Pace, Quine, and Lewis, modality understood as what's possible or necessary, not what is true in some or in all possible worlds, is not mysterious, right? It came very naturally for the reasons we saw earlier in the talk. Why is this form of an empiricism, someone may ask? Well, the idea is that the proposal focuses on properties of objects that can be detected via suitable instruments without reifying such properties. Note that I don't know what an electron is. I don't even know whether electrons exist given their size, right? What I can do is sort of study what these objects are in light of some instrumental access, but resist the idea of reifying the properties of electrons, right? So properties are here not meant to be understood in terms of abstract objects, universals, possible worlds, anything of that. These will just add metaphysics, a layer of metaphysical description to something that is far more straightforward, as we saw in the actual practice of the physics with the Dirac case and the Sakurai examples. So think about modalities just features, properties as just features of things, right? Breakable tables, negatively charged electrons, necessarily symmetric states, right? These are just features that things have. Whether they exist or not, and all those things, well, that's where realist and anti-realism realists may disagree, right? The point is we can make sense of that without adding an extra layer of metaphysics, right? Without saying, okay, when I'm talking about what's possible, I'm talking about something true in some possible world or the instantiation of some universe of some sort and so on. I'm resisting that. Finally, but also that this is a contingency first approach in the sense of Alistair Wilson. What needs to be explained is the necessary. The contingent, being ubiquitous, need no explanation, right? So what makes it something necessary is the fact that certain things are in place, and once they are in place, other things have to be in place, right? There are no absolute necessities on this view, right? And so in further development of the paper, I will argue when I engage with Bob Hale, why I don't think that there are absolute necessities, right? Necessities are always relative to other things that have to be assumed. So it's in that sense also that the necessary needs to be explained in terms of other things, but the contingent is just a feature of the world. So that's the kind of starting point here. So to conclude, modalities, for the reasons we've saw, modality is crucial for quantum mechanics, including the characterization of the quantum domain and the specification of the states quantum systems can be in. But the source of modality should not be understood in terms of conventions, models, or essences. Rather, it should be understood in terms of the relevant objects and their properties. Empiricist modalism offers a deflationary account of modality and its source in the context of quantum mechanics, of course, and elsewhere. Needless to say, far more needs to be argued in its support. But I think it's, in principle, a possible way of it's a possible way of accommodating this cluster of issues. Thank you very much.
Thank you very much, Otávio. Very interesting and thought-provoking talk as always. Matteo, the first question, please. You're muted. Sorry, Matteo.
Sorry, I thought I muted it. Okay. Can you hear me now? So let me start again.
Yeah.
Thank you, Otávio. That was really great. I will have a bunch of different questions, but I will focus on just one thing. I'm not entirely clear how your conception of modality works. On the one hand, I'm wondering, isn't the having of primitive model properties a sort of kind-defining feature. If it is, it seems to be essential.
Yeah.
So you seem to be caught in a circle at some point. And the other thing, you ended up saying...
Can I say
yes,
something
sure,
about
sure.
that? So, yeah, of course, I would resist couching the modality in terms of a kind, right? Because that of course, that would be that's Lowe's way of thinking about the subject matter, right? And but I think this is to add exactly the kind of metaphysical layer that I want to resist, right? As I try to argue for in the first half of the paper, Dirac, and Sakurai, and I could multiply the examples elsewhere, very naturally talk about the modal features of the objects they are studying. And I think, so the idea is focus on those things, right? So what these objects are, right? And of course, once objects are the way they are, right, they will have relations with other things, right? That's where the network of connections of what's possible, what's necessary for them will emerge. So rather than think about a kind, right, think about, don't move up, just stay where you are, right? You have objects and properties. These are the things that are there, right? In specifying these objects and properties, you're already setting up what the modal properties in question are, right? So it's easier to think in terms of the table, right? My table has a property of being breakable, right? Given the constitution that it has. Same thing goes for an electron, right? Given what the connection that electrons have with other electrons, and they will be able to enter in such states or not able to enter in other states, right? And that's the modality will come out from that.
Sorry.
Yeah, no, then you say, well, but all right, I'm going to explain that by saying, oh, electrons, because they are things of that kind, now I know that they behave that way. I said, well, it just gave me a name, right? I'm not sure that actually explained anything beyond what I just said, right?
Well,
So
I don't care that much about using the terminology of kinds. Right. The worry is that your examples are about specific things, like one table, one electron, one particular state, while in physics we need general talk, fermions, tables. And my worry is that if you focus as an empiricist on the specific fact that you have in front of you now, then you don't get the typical description of things that you get in physics. Unless, and this is the second half of my question, you put modality into the theory and you go back to conventionalism, which I wanted to defend a little bit because I think you've been too nasty against conventionalists. It's not necessarily a matter of meanings. As far as I understood, people like Reichenbach or Poincaré, in that for them, conventions are basic things that we take to be true, without being open to discussion. So it could be that we don't know what a fermion is. This is our starting point. We divide particles into two kinds and blah, blah, blah. This is just an axiom. Let's call it an axiom. Right. It's not a linguistic convention.
Well, yeah, but then we have to ask, okay, why are you posing that particular axiom? Right? If you say, look, this is my starting point, this is an effectively functioning as a linguistic convention, right? I'm going to use the term fermion now as something that, satisfy those relations here given the axiom. In fact, that's the way some people may interpret, for example, axioms in set theory, right? You tell me, okay, what is the membership relation? So, well, whatever satisfy the axioms of Zermelo-Fraenkel set theory, right? And don't tell me anything more because all I know is what follows from those things, and that's my grasp.
Well, of course, these linguistic conventions are constrained by experience. This is the basic point. As an empiricist, you should be happy.
Good, except that I want to constrain from experience from the get-go. Right? There is a reason why these axioms are introduced. they grasp certain properties of the relevant objects. It's not a matter of convention, right? It's a matter of conveying an understanding of the objects in question, right? It seems to me conventionalism is not strong enough for that. Right? At least that's the way but your point is very much well taken. So maybe I should, I should have been a little more sympathetic with the conventionalist. But thank you, Matteo.
Thank you.
Thank you, Matteo. Thank you, Otávio. Well, let me propose something to you. We have only 5 minutes and 3 questions. We will not be able to make all of them. So what if we extend our meeting so that everyone can get the chance to ask?
Finish the discussion.
Yes. So no more questions, but let us finish with this. Okay. Thank you, everyone. So, Chris, you have raised your hand, and then you drop it, and then you. So, okay, please.
So, very interesting talk, Otávio. Thank you so very much, because we're also working with Raimundo, who also raised his hand about Dirac. So we're really interested in this. It's really fantastic. So, of course, I mean, Dirac. I think that there is a consistent part of Dirac's work, because essentially what he claims in a very positivist manner is that in his book, from where you were taking the quotations, that physics is only about observables. Physics should be only concerned with observables. We should forget about pictures. Just let's forget about pictures, and he also claims, okay, what is quantum mechanics talking about? It's talking about superpositions, and we have no relation of this mathematical weird elements to a representation. Surely not in classical terms. So it has. He really understands that a superposition has nothing to do with. It cannot be represented in classical terms.
Right.
So that's the consistent part for me. Now I introduce the inconsistent part, which I think Bohr, which is. I mean, he makes exactly the same move as Bohr does in his atomic model of the atom, which is, okay, I have an algorithm. I have certain phenomena that's described by this algorithm. This algorithm is completely inconsistent. It's a mess. And now I'm going to give you a picture. This algorithm, it's like a small solar planetary system. But space is discrete. And you can disappear and appear, so the planets can appear and disappear. So, I mean, it doesn't make sense. It really doesn't make sense. But at the same time, he's able to introduce a kind of pictorial image in the minds of physicists. So you kind of immediately tend to think that you're understanding something, that you have a picture of something. Okay, so an atom is something small. So already talking about smallness implies a picture. Implies a metaphysical picture. You are introducing particle metaphysics, atomism within the debate, within the discussion, because of course small. Of course you can provide the definition of Dirac, but of course small is also related to something in space and time, because small relates to big, and we are supposed to be the big guys, right?
Yeah, but not. I think Dirac was very careful. That's why I went into pains to present.
Wait. So I finished my question. So okay. so you are introducing objects as justifying the modality. So it's relating to the modality, but you don't have the objects. You did not define them. You don't even believe in them. So I see this kind of inconsistent loop in the way you.
No, I can see that. That's a great question. Thanks a lot, Christian, for that. So, yeah. So first with Dirac, Dirac is actually very interesting. I find, right, because he's in a way he's very consistent in principle, right? He will look at he says, look, quantum mechanics is this sort of equations, right, of motion, and that's the way he looks at it. Right, and he wants, okay, let's find those equations. If he could, he would just apply classical equations throughout. He realized he cannot, so he looks for other equations. You're quite right. He's sort of separating. Right? We have these superpositions. So these are fairly unique quantum phenomena, he thinks. So these are different. We need to move away from the classical. But he wants to offer an account of the domain of the quantum that doesn't specify anything about the constitutive nature of the things that he's considering, right? That's why he just talks about, well, something is small if the observation involves a disturbance that cannot be made negligible. So if you present in that way, to the extent that you're observing, certainly, yes, you're assuming that there is, not that it exists, but that there is something there that is being observed. What it is not settled, right? No, the experiment doesn't specify that, right? What the constituents are that of the thing, it's also left open. So in that way, I think you can navigate in a very deflationary way, which that's why I'm suggesting with the modalist empiricist. You don't need to specify anything about the object, right? Not even if it exists, right? Think of it as an object of quantification, right? So that's something in the domain that you are studying. Whether it exists or not is a separate issue, right? Now, this thing, right, is supposed to have some properties. In fact, it's because it has some properties that you're able to observe it. And if it's small, when you observe it, you disturb it. And there's no way of not disturbing in some non-negligible way. And you can do that without saying anything in detail about what these objects are.
Yeah, can I say something? Because I mean, the very point that you're making, that you have a system with properties, is what is at stake in quantum mechanics, right?
Yeah, but then don't interpret system with objects with properties in a metaphysically loaded way. Right, that's what you need to hear the words.
So how could I do it?
That's why I look at specific examples, right? So I think about an electron, right? Now
you're talking about a particle, right?
Well, no, you're interpreting. If you say it's a
particle. No, you're saying you're actually.
No, I'm just talking about an electron. Right? Don't overinterpret my words, right? So you have an object. Now, being an object, it means that it's just in the domain of your quantification. What that object is, I don't know. There's disagreement, right? There are particle interpretations, there are field interpretations that say there are no such things. Then you need to recapture them in some way. All of that is up for grabs, right? Quantum mechanics is just describing these things at this very low level, just objects and their properties. Right? So don't add a layer of metaphysics.
I would say you don't have that description. That you only have quantum superpositions. I would agree with Dirac.
Yeah, but you have quantum superpositions, no question. But you have electrons that and they are in the superpositions. So even though you don't know what the electrons are, and that's the beauty of the way that he defined quantum particles. He left completely unspecified. They are just small, right? That's the elegance of the conception he offered. It's a very deflationary understanding of objects and the properties. And I think that's exactly the way that an empiricist, modalist would say, yes, that's the way to go, right? You just don't go much beyond what is needed just to specify the domain of what you're talking about. Don't overstand. Because the moment you do that, then you get lost in the metaphysics fog, right? And that's where the troubles start. So that's the idea. Right?
Thanks a lot. I guess we'll continue.
Thank you, Chris.
Oh yeah,
thank you, Otávio. Sure. Moises, your question, please.
Thank you. Thanks for your very interesting talk, Otávio. So I think we discussed maybe some of our disagreements about modality at some point. That I find, for example, like mathematical structures more intuitive than modality, And I mean, I remember this paper that you have with Tsiolkovsky, but I want to like be concrete about the specific objection that I have with your, I mean, because before you go on to your position, you take a number of positions and you try to say why you don't think that they work. And I think, I mean, with regards to conventionalism, I also want to like go back to that argument, because I feel like the position that you are objecting against is sort of anachronistic, because, you know, it's like the sort of position that identifies conventionality with analytical truths. I mean, like the sort of examples that you gave. And like there are some views on the, you know, in the market right now, which try to preserve the idea that a convention has something to do with us because we make decisions about what truths are conventional, but they are not to be identified with analytic truths, because, you know, worries about whether you can ground like the infinitary truths of logic or math in something like analyticity, right? So stuff like that. So, so for example, on some of these views, for example, Sider has some discussions of these views. An analytic truth is just going to be something which is true, and that we, you know, as inquirers or something like that, have decided to call necessary. So it's just going to be a certain truth of a kind K, and that's it, right? And then it seems like, for example, propositions of mathematics, propositions of logic, they are propositions which we take very seriously. We think many of them are, many of us think they are necessary. On this account, those propositions will be true, but they will only be necessary because we have decided to call them necessary. And then, okay, there's a further question about whether, you know, how deep are those truths, how general they are. So, for example, on this view, the fact that, you know, mathematical truths are reached so deeply, that's just because of the way mathematics is, but has nothing to do with necessity. So, for example, necessity just gets, you know, the necessary truths of mathematics just gets that property from this further fact, right? So, so I mean, I guess we on this line of thinking, we can extend this view to physical necessity as well, and I think that that's compatible with everything Dirac says and everything that you've said, because you can still think that there are truths that are grounded in the physical, you know, the smallness and the you know, largeness properties of these physical systems or physical structures. You can think that they are true, and moreover, you can think that they are very important to us because of the way in which we do inquiry, and then you can call them necessary. So I wonder whether you think, I mean, are there like further objections to those sorts of accounts of necessity that
yeah. Perfect. Thank you so much for this great point, because you're quite right. The view I'm considering and I was targeting is the early formulation of conventionalism. But there was a reason to do that and not look at the most recent ones, because at least the earlier view, there was an attempt at explaining what the source of modality is that would make something indeed necessary. Right? Because just the fact that we conventionally agree to take certain statements, say mathematical statement, as necessary, doesn't make them necessary, right? And that point is absolutely clear. So I don't think that would even answer the question about the source of modality. You're not taking modality seriously if you do that, right? It's not a matter of, okay, let's all agree from now on that the axiom of choice not only is true, but it's necessarily true. Right? So, okay, good. Now it is necessarily true. And so, what? Why? Right? So I want to know what is about the axiom that makes it so. Right? The early forms of conventionalism had an attempt to do that. Right? So, well, look, we have these conventions. Once you define the vocabulary in certain ways, it would follow that certain things have to be that way necessarily. So that's an attempt at answering the question. Now, conventionalism in the sense of, okay, let's just simply all agree on taking certain terms as or statements or proposition as being necessary, that's not really answering the question. So I don't think that that's even on the ballpark, right, to answer what was worrying me.
Right. Just like, can I just give a quick follow-up?
Yeah.
Really, really quick. So, so I guess I mean, you are right that this theory is not as ambitious as the old conventionalist accounts. But for example, on these views, I guess part of what people who defend these accounts will say is that, look, I'm not saying, for example, that the truths of mathematics or, for example, the truths of physics are not different truths from the truths of, I don't know, for example, economics or something like that. But then the claim will be, the claim should be understood about a claim about those types of structures and how, how general they are. So, for example, it's going to turn out that regardless of whether you are living in planet Earth or you're living in, the Andromeda galaxy, then 2 + 2 is going to be 4, for example, right? And then, but some truths don't go that deep. So on these views, we should look for, we might be inclined to call necessary such truths that, hold with greater generality, but that does not require any sort of, for example, account of possible worlds in a sort of reified way or essences or stuff like that. But it doesn't mean, and this is just the last point that I'm making. It doesn't mean that it doesn't distinguish between different kinds of truths, right, which is what your worry is about.
Yeah, but then look, it's not convention that is doing the work, right? If you say something is necessary because it holds no matter what, then it's not a matter of convention, right? This is supposed, so it's the arbitrariness of the truth that is making it necessary. Now we have a different answer. No, it's no longer conventionalism. Now that's a more interesting approach because now you're considering something about the objects. Okay, these are objects such that no matter where they are placed, no matter the conditions under which I'm considering, these claims about them will come out true. All right, now we are in the game, right? Or at least addressing something about the objects. But that's not a matter of convention anymore, right? So that would be something. Now, when you do that, you're going to start getting closer to the views that I want us to consider. Consider the objects. Why is it that it doesn't matter? The conditions and the statement in question will come out true, right? And I think that, okay, that's Moises. I think that's a better way of handling. And if we keep pushing it without adding the metaphysical layer, we end up with something like a modalist empiricism, right? So, and well, at least that's the claim, right? So,
thanks. No, that's. Thank you for your answer. I mean, I think I would resist the last step, but yeah, I'm sympathetic with everything else you said. But thank you. Yeah.
No, of course, I'm just joking. So.
Thank you, guys. Now, Raimundo.
Yes, thank you, Octavio. It was very interesting and very, very clear. So thank you. My comment my question is going to complement a bit Christian's comment.
Mm-hmm.
As he said, we are just now reading that same part of the Iraq book.
Good.
It's very, very interesting. I think it has a lot of problems, but it's very interesting. And I was just thinking about the idea of defining an supposedly absolute definition of small and big.
Mm-hmm.
And I think that this should maybe be interpreted in the context on the discussions about atomism. Because when Schrödinger starts to question atomism in regards to quantum mechanics, he goes back to ancient atomism and he says, it is not so strange that we are questioning atomism if we look back at the origin of atomism, because atomism was also, as Dirac was suggesting, a kind of solution, a postulate to the problem of infinite divisibility when applied to matter.
Mm-hmm.
So Dirac is telling you have to go to each time to a smaller thing to explain, and you go to infinity. So atomism is a way of resolving this, different from the Eleatic path, which is there's no division in matter. So in a way, it's very interesting because Dirac is giving a different answer to that same old problem, different from the classical atomist one. Let's not postulate simple bodies, but let's postulate that there is a limit to observation. So this will define an absolute meaning of smallness and of bigness, which is similar, I think, to Bohr's solution. So you say there is a limit to the observation. So he's drawing a limit to our capacity of representing, quantum phenomena. And in this way, I think he's not questioning the classical concept, but he's saving the classical concepts. Because we are saying we cannot represent these quantum things, so he keeps on talking about atoms. So this, he's not really changing the classical language, but he's helping, keeping this language. And I think this shows that, for me, in Dirac's book, there's as Christian said, there's a contradiction between an empiricist's supposedly account and his continuous atomist language that is not just a way of talking. It's a way of thinking and a way of perceiving. It informs his interpretation of possibility in quantum mechanics as the possibility of finding a particle in a given location. So I find it very interesting, this solution of the problem of infinite divisibility, very interesting in the history of science, I would say, but at the same time very problematic. And I see that Dirac's objective is really to maintain this classical concept, to stop, this new concept for representation of this quantum phenomena. You see what I say?
Yeah. No, this is very interesting, Raimundo. Thanks for the question and the comments. And I think we may read Dirac differently, right? Because I think that what he's trying to do is to identify what's unique about quantum mechanics. In fact, that initial portion of the book that I quoted at length is him saying about the necessity of quantum mechanics, right? Where it needs to break down with classical modes of thinking. So I think he wants indeed to say, look, there is something quite different going on here, and we need to acknowledge that. And interestingly, I wouldn't read him as an atomist. I think actually the definition of small he has is set up in such a way that you don't have any stake on the debate about whether there are atoms in the traditional sense of things that have no divisions. Because the only break he gave is it's small or big. And it's small are those things that under observation are disturbed in ways that you cannot make negligible. That's compatible with there not being anything atomic at all, right? Once you're small, you keep going on forever, for all you know. So his definition, I think, leaves him quite independently of any commitment to atomism. And I thought that was actually one of interesting ways of the way he's framing it. It's really very deflationary. And I think Dirac is very careful on how to interpret certain things, right? And of course, that's how he managed to discover the positron, right? Looking for reasonable interpretations of pieces of mathematics. The first two ones he tried didn't work, and the third one did, right? So he ignored the negative energy solutions and said, well, this is just like classical mechanics, let's forget it, right? Then looking at what we now call the Dirac equation, and said, well, no, wait, don't ignore, right? These negative energy solutions stay for holes in space-time. Then Heisenberg and Weil immediately point out, look, according to this whole theory, electrons and protons have the same mass. Of course, this is just empirically wrong. So 2 years later, he said, oh, scrap that, right? What we have here is a new particle that has the same mass as the electron, but the opposite charge. And Anderson 2 years later found something that with a lot of work can be reinterpreted as being the positron. So the point here is, it's part of the way he works, the Dirac work, is to interpret, find reasonable interpretations of mathematical formalism. And he's doing that with quantum mechanics all the time. But he wants to be very careful when he's doing that, right? And I think that's why he set up the small in the way he did, right? The big and small. So I think he's completely neutral on whether atoms in the traditional sense exist or not. It's a definition that allows quantum mechanics not to be an atomic theory, right? In the traditional sense, it's compatible with one, but it doesn't have to be one. It's a theory of the small, right? And I thought it was brilliant. It's really interesting what he did, right? And it's entirely modal, up to his neck, right? So that's what I find very telling about the way that he's conceptualizing and understanding quantum mechanics. So these guys were great. It was really interesting. It's always pays to reread them.
Always interesting.
Yeah.
And, well, I hope you can. I don't think. I think that maybe throughout his book he tends to suppose an atomist way of thinking. Maybe if it's a bit unconscious, but maybe we can continue to discuss that with Christian. We are working on it, so we'll continue this.
Yeah, please do keep me posted. I have a lot of interest on that, of course.
Okay, thank you.
Yeah.